Welcome back to an introduction to real analysis. We're now in Chapter 5, Section 5, Improper Integrals. So often, it's going to be necessary to integrate a function over the entire real number line, or perhaps an unbounded interval going off to infinity in one direction, or maybe you want to integrate a function that is unbounded on an open interval. Now, for such intervals or functions, the Riemann integral is not strictly defined, but we're going to write down the integral anyway in the spirit of Lemma 5.2.8. These integrals are called improper integrals. They're not properly Riemann integrable functions, and are limits of integrals rather than the actual integral itself as written. So here is our first definition. Suppose you have a function f on the interval a to b, which is closed on the end a but open at b. And for all c in between, f is Riemann integrable on the interval from a to c, including both endpoints. Then we define the integral from a to b of f to be the limit as c approaches b from below of the integral from a to c. In other words, provided that the function can be integrated from a to any stopping point up to b, but not necessarily including it, you simply take a limit of that process and define that to be the integral from a to b. If that limit exists, of course. Similarly, suppose a function f is defined beginning at the real number a and then off to the right, and no matter where you stop to the right of a, the function is Riemann integrable on the interval from a to c. Then you can take the limit as c goes to infinity of the integral from a to c and define this to be the integral from a to infinity, again, if that limit exists. So some terminology. If that limit exists, you say the improper integral converges. If it doesn't, you say it diverges. You can also define improper integrals approaching the left endpoint or going off to minus infinity as a sort of quasi-endpoint. Now, there are some issues that come up if both endpoints are improper, if you want to go off to infinity in both directions, etc. For now, that is not covered by our definition, but we will address that later. Now here we have lemma 5.2.8 from a previous section. If you have a finite endpoint b and the function f is bounded, then this lemma basically says that this new definition is completely consistent with the existing definitions and nothing has really changed. What is new is that you can now apply this definition to unbounded functions. So the following several examples are so useful that we're going to state it as a proposition. Proposition 5.5.2. If you want to integrate 1 over x to the p, note that this is unbounded as x approaches 0 depending on the value of p, and the interval is unbounded if you want to let it go to infinity. So we state two different things. If you want your improper integral to start at 1 but go off to infinity, it converges to 1 over p minus 1 when p is larger than 1, otherwise it diverges. Instead, if you want to integrate from 0 to 1, then this diverges when p is bigger than or equal to 1, and converges to 1 over 1 minus p when p is less than 1. Let's just work through a computational proof here. When p is specifically exactly 1, then you can just apply the fundamental theorem of calculus. Remember, the definition essentially of logarithm is this integral. And you get that the integral from a to b of 1 over x is log b minus log a. And we also know that the logarithm function is unbounded both as a approaches 0 from above and as b goes to infinity. So both of these limits will go to infinity. So specifically for p equals 1, you get divergence for both improper integrals. When p is not 1, then you just anti-differentiate, apply the fundamental theorem of calculus. Works out as follows. The integral from a to b of 1 over x to the p is b to the 1 minus p minus a to the 1 minus p all over 1 minus p. Now, if p is larger than 1, then 1 minus p is negative. This denominator, incidentally, of 1 minus p is basically irrelevant now that we're going to be taking some limits. I mean, for the exact value it matters, but whether the limit converges or not, this is not really the key point. Rather, these exponents being positive or negative will make a difference whether a and b are going to infinity or 0. So if 1 minus p is negative, then b going to infinity does not present any sort of problem. You're taking larger numbers to a negative power, that converges to 0. In this case, we merely compute this limit to be 1 over p minus 1. And now we've established this convergence right here. However, if p is less than 1, then 1 minus p is positive, and now you have larger numbers to a positive power, that goes to infinity, and you get divergence. So p bigger than 1 converges, p less than 1 diverges, p equals 1 diverges. We've established all relevant claims for this left part. So let's move on and look at the improper integral from 0 to 1. Now we start from the same place. The integral from a to b of 1 over x to the p is b to the 1 minus p minus a to the 1 minus p over 1 minus p. But everything is essentially reversed now that a is going to 0 from above and b equals 1 is constant. When p is less than 1, you are raising a to a positive power. So raising something to a positive power and letting a approach 0 from above, that just goes to 0. In which case this all computes down to 1 over 1 minus p in the limit. But when p is larger than 1, you are now attempting to raise something to a negative power and letting that a approach 0 from above, that goes to infinity, in which case the improper integral diverges, and that finishes the proof of the right side here. We're going to state the following proposition for tails just as one type of improper integral, though the proof is basically straightforward and the same for other types of improper integrals as well, meaning those bounded interval types. We're just reclaiming proposition 5.2.2 for improper integrals, that integration on two adjoining regions can be combined together into a single integral. So here's proposition 5.5.3. Suppose f is defined on the interval from a to infinity, and it's integrable on every interval therein. Then for every b larger than a, the improper integral from b to infinity converges if and only if the original improper integral from a to infinity converges, in which case you get this additivity. The integral from a to infinity is the integral from a to b plus the integral from b to infinity. Okay, so let's get proven. Let c be an arbitrary real number larger than b. Then f is Riemann integrable from a to c. Remember, we've assumed that the function can be integrated on every interval from a to a finite stopping point. So by prop 5.2.2, the integral from a to c can be expressed as the integral from a to b plus the integral from b to c. And now we just need to take a limit as c goes to infinity. Okay. Now, non-negative functions are in general easier to work with, as the following proposition is going to demonstrate. Exercises will show that this proposition in fact only holds for non-negative functions. Analogs exist for other types of improper limits and are left to the reader. So here's this proposition. Take a function defined on this unbounded interval from a to infinity. Suppose it's non-negative and it is Riemann integrable on every interval from a to b. Then the integral from a to infinity is just the supremum of all of the nice definite integrals from a to x. Similarly, if xn goes to infinity, then the integral from a to infinity of f equals L if and only if the integral from a to xn of f converges to L. What's important to point out here is that this sequence xn is arbitrary. The improper integral converges to L if and only if this sequence of values converges to L, and this sequence xn is any sequence going to infinity. Now, this does hold for non-negative functions. As mentioned before, it's really quite important that your function is non-negative everywhere. Okay. Now, in that first item, that the integral from a to infinity of f is the supremum of these finite integrals, we are going to allow for the case that this set is unbounded and the supremum is plus infinity. Note that since the function little f is non-negative, if we define the function capital F of x to be the integral from a to x of f, that is an increasing function. Suppose y is bigger than x. Take capital F of y minus capital F of x. Here we have the integral from a to y minus the integral from a to x. That will leave behind the integral from x to y. Since f is non-negative, this integral is non-negative. We have also assumed it's Riemann integrable on every interval in question here. In other words, f of y is bigger than or equal to f of x. So this function capital F is increasing. The first item now follows from prop 3.6.2. If you have this increasing function, this limit is merely the supremum of the values. There we have it. The second item now follows from exercise 3.5.7. We're going to omit the details. It is left as an exercise. What is important, as I mentioned before, and what really makes this key, you have a non-negative function. What makes this a nice, powerful result is that this sequence xn is any sequence going to infinity. If you can compute the sequence of definite integral values and show convergence to L, then you have computed the value of the improper integral. Now prop 5.5.5. Suppose f and g are both Riemann integrable on every interval from a to b where b is larger than a. Assume also that the absolute value of f is less than or equal to g of x for all x bigger than or equal to a. Note that since the absolute value of x is certainly bigger than or equal to 0, this necessarily implies that g of x is non-negative. Then if g has a convergent improper integral from a to infinity, so does f. And furthermore, the absolute value of the integral from a to infinity of f is less than or equal to the integral from a to infinity of g. All right, so assume a is less than or equal to b is less than or equal to c. F and g are both integrable from a to b and from a to c, so they're integrable from b to c. And since f is bounded above an absolute value by g, then f is bounded above and below by plus or minus g. These inequalities can then be integrated from b to c. The -1 can be factored out here, which means that the integral from b to c of f is in between plus or minus the integral from b to c of g, which is to say that its absolute value is less than or equal to the integral from b to c of g. So here's what we established on the previous slide. Now let epsilon be arbitrary and recall prop 5.5.3 that these unbounded interval improper integrals have the same additive property on their regions that nice proper integrals did. Then the integral from a to infinity can be expressed as the integral from a to b plus the integral from b to infinity. So now let's take a limit as b goes to infinity. That will establish, since b is going to infinity, we'll recover this improper integral, that this tail piece must be converging to 0. So the limit as b goes to infinity of the integral from b to infinity of g must be 0. In other words, we can choose capital B large enough so that this improper integral is less than epsilon. All right, so here's everything we've established so far. Again, under this umbrella that a is less than or equal to b is less than or equal to c. The integral of f in absolute value is bounded above by the integral of g. We also have picked capital B large enough so that the improper integral of g starting at capital B is less than this arbitrary epsilon that we picked. Now g is non-negative, so if we now force little b to be bigger than or equal to capital B, we will have that the integral from little b to c will be less than or equal to the integral from little b to infinity, but that's going to be a subset of capital B to infinity, and that integral is less than epsilon, so this integral is less than epsilon as well. So now let's let x sub n be a sequence of numbers going to infinity. Let capital M be large enough so that eventually every term of this sequence, past index capital M specifically, is larger than b. Then, for two indices, m and n, both past this cutoff point, the integral from a to xm minus the integral from a to xn will simply be the integral from xn to xm. Now I have this is less than or equal to the integral of g, but note that this is larger than capital B, and this is a nice finite cutoff. So as argued right here, that's less than epsilon. In other words, the integral from a to xm of f minus the integral of a to xn of f in absolute value is less than epsilon for any two indices past capital M. Which is to say, we have made a Cauchy sequence, specifically the integral from a to xn of the function f. Since this is a Cauchy sequence, it must converge. So for any sequence of xn's going to infinity, this sequence of integral values converges. Now suppose I have two sequences going to infinity. They both have to have convergent sequences of integral values. Suppose they converge to L1 and L2. Now I make a new sequence just by alternating them, x1, y1, x2, y2, and so forth. Since the x's are going to infinity and the y's are, so is this interspersed sequence. Therefore, the sequence of integrals along the sequence goes to some limit, but every other term here is given by taking a upper bound of integration to be x sub n, that's converging to L1, and every other term is converging to L2. So if every other term is converging to L1, every other term is converging to L2, but overall we're converging to L3, these all have to be the same number, which is just to say that it didn't matter when we took two different sequences, xn and yn going to infinity, these would both be converging to the same thing. Okay, so for any sequence going to infinity, this sequence of integral values converges to the same thing. If we denote this shared limit as L, we now see that the improper integral from a to infinity of f must be L. And furthermore, since for each nice bounded interval from a to c, the absolute value of the integral of f is less than or equal to the integral of g, we can just take a limit as c goes to infinity to establish this final claim right there. Moving on to example 5.5.6, let's compute this silly little improper integral. Now, we'll establish a chain of inequalities. First, in absolute value, the sign of anything is less than or equal to 1. So just replace this sign function with a 1. Now, x cubed plus 1 is bigger than x cubed. So 1 over x cubed plus 1 is less than just 1 over x cubed. Finally, since we're only letting x start at 1, 2 is less than or equal to 2x. Note that this is just 3x, and I can cancel that shared factor of x. So in absolute value, the thing that we are integrating is less than or equal to 3 over x squared. The integral of 3 over x squared converges on the interval from 1 to infinity due to the aforementioned p test. Since we're integrating 1 over x to the p, and p is larger than 1, the improper integral from 1 to infinity converges. The fact that it's being multiplied by 3 is functionally irrelevant. We therefore conclude that our integral here also converges. But we don't necessarily know to what. Okay, it's definitely got to be converging to something less than 3 in absolute value, but what exactly, I have zero idea. Example 5.5.7. When doing algebraic manipulations on improper integrals, do be careful. Consider the function 2 over x squared minus 1. This is continuous once x is larger than 1, so let's just start the improper integral at 2. 2 over x squared minus 1 is more or less the same function as 1 over x squared as far as convergence or divergence of certain things is concerned. So that improper integral does converge. You can show that. You can also verify that 2 over x squared minus 1 is just flat out equal to 1 over x minus 1 minus 1 over x plus 1. But you cannot replace this integrand with this and then split it up into these two improper integrals. This improper integral converges, but each of these diverges. So you have an issue there. So be very careful when doing that kind of algebraic manipulation with improper integrals. You have to make sure that every term still converges. Moving on to definition 5.5.8. Suppose f is a function that is Riemann integrable on all intervals. Then, if the limit exists, we will define the integral from minus infinity to infinity as the limit as c goes to minus infinity of the limit as d goes to infinity of the integral from c to d. Also, suppose that you have a function that is Riemann integrable on all subintervals, including endpoints of the interval ab, not necessarily including endpoints. Then you can define the integral from a to b of f to be the limit as c goes to a from above of the limit as d goes to b from below of the integral from c to d. You can similarly define improper integrals for these sorts of variants where you would now take a limit approaching a from above and going to infinity and a limit going to minus infinity of a limit going to b from below without explicitly writing out these variants. The real point of the previous definition is we have a double limit, a limit of a limit. And there is a very particular order specified in that definition. Does the order matter? We hope not, right? If I take the limit as one side goes to minus infinity and the other goes to plus infinity and I reverse the order, I really hope I don't just get a different answer. So our first order of business is to prove that it doesn't actually matter which order you take these limits in. We wrote it down in one particular order, but we will show that if that converges, it also converges to the same thing in the other order. That's coming up. First, let's look at example 5.5.9. We're going to take the improper integral, both sides going to plus or minus infinity, of 1 over 1 plus x squared. Now, the order that we wrote our definition, we have to take the limit as a goes to minus infinity of the limit as b goes to infinity. This, however, just works out to be an arctangent. So first, let's take the limit as b goes to infinity of arctan b, where this is remaining constant. That's going to produce a pi over 2. Now, this is constant. We take a limit as a goes to minus infinity. We get a pi over 2 minus pi over 2, which is just pi. Note, however, that this pi can be recovered as this limit, which would produce a pi over 2 minus pi over 2. And then I can reinstate this as the limit as a goes to minus infinity of arctan a. In which case, our original order of limits could exactly be reversed. In this particular example, we need to show that this is a general phenomenon. So here is prop 5.5.10. Suppose f is a Riemann integrable on all intervals. Then this limit exists if and only if this limit exists. And note that all we do is switch the order of the two limits, and we're going to say that if one converges, so does the other, and the two are equal. So in this case, we can in fact compute this improper integral by simultaneously taking a limit as the upper limit goes to infinity and the lower limit goes to minus infinity, controlled by the same limit. So while we did define it as a double limit in a particular order, if that converges, then so does the other order, if and only if, in which case you could have done both simultaneously. It's proven. So without loss of generality, let a be negative and b be positive. Note a is going to minus infinity and b is going to infinity in these limits. So let's suppose that this first expression converges. So this expression right here converges. Now the integral from a to b may be broken up as the integral from a to 0 plus the integral from 0 to b. As far as this limit is concerned, this first term is a constant. So let's distribute that limit as b approaches infinity across those two terms, and then distribute the limit as a goes to minus infinity across both terms. So here's where we are right now. We now have the limit as b goes to infinity of a constant, so that's just that constant. So now I just have the limit as a goes to minus infinity. Similarly, as far as this limit is concerned, this is constant. It has nothing to do with a, so I will recover that constant. So then, this limit as a goes to minus infinity of the integral from a to 0 is a constant as far as b is concerned, so I can throw this limit on it without affecting it. Inside this limit, this has nothing to do with a, so I can throw this limit onto it without changing its value. And now in both terms, I have these limits in the same order, so I can bring it back out. So there's not much going on here. It's really just a bunch of trickery involving algebraic manipulations of limits and keeping track of which integral is constant with respect to which variable a and b. But at the end of the day, we interchanged our order of limits without much of an issue, assuming that all of these things had limits to begin with. This is why we began by saying assume that this limit exists. And now we showed that it's equal to this one down here. You could also do all of this in the opposite order to switch your limits back. So if one order converges, so does the other, and vice versa, and they converge to the same thing. So now let's get on to the last claim. So we have the integral from minus infinity to infinity. By definition, it's written in this order of limits. Using the same tricks as in the previous proof, this integral from a to b, we're going to split up as the integral from a to 0 plus the integral from 0 to b. The first part only has to interact with this limit, and the second part only has to interact with this one. And now, a going to minus infinity and putting an a down here is the same thing as letting a going to plus infinity and putting a minus a down here. And now, in the second limit, instead of calling this b, I could just call it a. In which case I can now recombine these. And again, not much to it, just a bunch of algebraic manipulation with limits. So another example to point out that you have to be careful doing algebraic manipulations on these limits if you don't yet know that the improper integrals converge. Consider the sine function, not the trigonometric one, but the function that for positive numbers spits out a +1, negative numbers spits out a -1. Technically, the sine of 0 is 0, but the value of a function at a single point doesn't really have anything to do with integration. Now, this function is -1 for negative numbers. So if a is negative, then the integral from a to 0 will simply be a. Okay? And if b is positive, you now are integrating from 0 to b, +1, which gives you a b. So certainly, both of these diverge as a goes to -infinity and b goes to +infinity. But if you attempt to combine them into the same thing here, you're now integrating a function from -a to 0, which is -1, and then from 0 to a, which is +1. So you have these balancing out of the two regions, and you will simply get 0. And there's a nice limit that works out there. So in the previous proposition, you could only do this computation to compute the improper integral if you knew that the improper integral converged as originally defined, which in this case it will not. So now another example. This is going to be a fairly lengthy example. It's the sinc function, which is sine x over x. Okay, the limit as x approaches 0 of sine x over x is 1. So this function is nice and continuous, but we're not really going to get into that. What we won't exactly show, but is true, is that the improper integral of the sinc function is pi, but if you take its absolute value, it diverges to +infinity. Loosely, what's going on here is that you have little bits of negative area and little bits of positive area and little bit of negative area and so forth. The size of these peaks and valleys is decreasing more or less like 1 over n. So in the original integral, this looks like the alternating harmonic series. You basically do a plus or minus 1 over n. But in absolute value, you would just do a plus 1 over n at every step. So this is sort of like the alternating harmonic series converging, whereas the harmonic series diverges. Now we're only actually going to focus on showing that this function is integrable from 2 pi to infinity. We're starting at 2 pi just as a choice. What's really important is we're avoiding what's going on near 0 because clearly there's something a little weird happening there. But because the function is bounded and continuous on the entire real number line, omitting a specific finite little piece doesn't really affect whether the improper integral converges or not. We're also leaving as an exercise showing that the absolute value of this function is not integrable. Now let's look at an interval going from an even multiple of pi to the next odd multiple of pi. So from 2 pi to 3 pi, from 4 pi to 5 pi, and so forth. On these intervals, the sine function is positive, and the number you're dividing by goes from even multiple of pi to odd multiple of pi. So our sinc function is bounded above and below by a straightforward sine function divided by two different constants. Similarly, from an odd multiple of pi to an even multiple of pi, you more or less have the same thing, except that the sine function is negative. So with those previously established inequalities, you can just integrate the sine function divided by those two constants to get some nice bounds on the integral of our sinc function. Specifically, from an even multiple of pi to the next odd multiple of pi, the integral of sinc is no bigger than 1 over n pi. Notice that this n is this lower bounds multiplier divided by 2, and bigger than or equal to 2 over this upper bound times pi. Similarly, on the regions where your sine function is negative, you get something very similar, just with a -1 or -2 on top. And notice that this n plus 1 here is this upper bound divided by 2, not the lower bound divided by 2 as it was here. Okay, because your numerator of sine function has flipped from positive to negative, you're essentially reversing your bounds. So in absolute value, by the way, we would now say that this function here is bigger than or equal to some stuff that's really looking like, on both sides, 1 over n, more or less. There's how you get that the absolute value of the sinc function diverges. Think back to an earlier proposition that had to do with integrating non-negative functions. Again, details are left as an exercise. Okay, so here are the inequalities that we have established for our sinc function, not an absolute value. Just for convenience, because I don't want to keep writing these integrals, I'm defining capital S of x to be the integral from 2 pi to x of the sinc function. So here is our function capital S of x, combining the fundamental theorem of calculus, stuff from the mean value theorem about where functions are increasing or decreasing, also the first derivative test. The function s is increasing where its derivative is positive, and its derivative is the sinc function, which is positive from even multiple of pi to odd multiple of pi, and it's decreasing from odd multiple of pi to even multiple of pi. Furthermore, because the derivative, the sinc function, changes from positive to negative and negative to positive at all of these points, you have local maxes at every odd multiple of pi and local mins at every even multiple of pi. So this function s of x, we can really clearly see as you track out multiples of pi goes local max, local min, local max, local min, local max, local min, and so forth. So let's look at the value of this capital S of x function at two successive local maxima. Local maxes happen at odd multiples of pi. So let's look at capital S at an odd multiple of pi. So remember that capital S is the integral of the sinc function. So if I integrate it from 2 pi to this number, I can instead integrate it to the previous odd multiple of pi, plus the integral from that odd multiple to this even multiple, plus the integral from this even multiple to this next odd one. So I've just taken this integral from 2 pi to this number here and broken it up into these three pieces. Now this integral, you have to flip back to the inequalities we established before. It's going from an odd multiple of pi to an even multiple of pi, is less than or equal to -1 over this upper bound over 2 times pi. But this one here, going from an even multiple of pi to the next odd one, is less than or equal to +1 over this lower bound over 2. And notice these exactly cancel out. In other words, the local max at 2k plus 1 pi is no bigger than the local max at 2k minus 1 pi. So the next local max is always getting smaller than the previous one. So the values at local maxes are a non-increasing sequence, and similarly, the values at local mins are a non-decreasing sequence. So looking at one local max after another and seeing that the values at these local maxes are not getting bigger, you conclude the value at a local max is in fact the supremum of all values you will see from that point forward. Similarly, the value at a local min is the inf of the values that you will see from that point on. So the values at each local max and the values at each local min, which simply occur at multiples of pi, are respectively the sup and inf of all values seen from that point on. So now what we can say is that the lim sup of the function, the limit of the sup of the function capital S, is merely the limiting value of these local maxes. And similarly, the limit of the inf of this function capital S is the limiting value of these local mins. Finally, our sinc function sine x over x, a quick squeeze theorem, tells you that this function goes to 0. I have a nice continuous function approaching 0. For any fixed interval length, if I integrate this function from x to x plus d, because this function is going to 0, it is bounded above and below by plus or minus epsilon, which makes the value of this integral bounded above and below by plus or minus d times epsilon. So taking this limit, since this is converging to 0, will converge to 0. Specifically, when d is equal to pi, we find that the value of a local min and max, the adjacent ones, the distance between them is converging to 0. So between our maxes and mins, the distance between them converges to 0. Therefore, the lim sup, in other words, the value of the local maxes, and the lim inf, in other words, the limit of the value of the local mins, are converging to the same thing. So now we have the lim sup of s and the lim inf of s are both equal to each other. In other words, it has a limit. But remember that capital S was merely the integral of the sinc function terminating at x. So if I can take a limit as x goes to infinity here, that's exactly the improper integral. Now prop 5.5.13, the integral test. Suppose f is defined from k to infinity, which is a non-negative, non-increasing function. Then a series made out of values of f at integers converges if and only if the improper integral converges, in which case the series minus the improper integral, series and improper integral both beginning at k, is non-negative but is no larger than f of k. Okay, there's really one key observation here. Since the function is non-increasing, on an interval from k to k plus 1, the smallest value occurs at the right endpoint, whereas the largest value occurs at the left endpoint. So f of x is in between these two values on this interval. So if I integrate f of x between k and k plus 1, it's bigger than or equal to the value at the right endpoint times the width of the interval on which I just integrated, which is 1, but it's less than or equal to the value at the left endpoint times the same width. Now we start chaining this together. F of k bigger than or equal to integral from k to k plus 1, bigger than or equal to f of k plus 1, bigger than or equal to integral from k plus 1 to k plus 2, bigger than or equal to f of k plus 2, and so forth. We continuously compare the value of a function at an integer to the value of the integral between two integers. So we have this chain of inequalities, and if we elect to terminate this chain of inequalities at an integral, what we now have is value bigger than or equal to integral, value bigger than or equal to integral, and so forth. So if I add up all of these f of n's from k to k plus m, and I take away the last one, so I have f of k plus f of k plus 1, ultimately stopping here. Okay, so I have added up all of these values of f. That is bigger than or equal to this integral plus this one all the way to plus this one. But now I glue together these regions from k to k plus 1 to k plus 2 all the way up to k plus m. So on the one hand, stopping my sum here is bigger than or equal to this integral. Okay, but stopping the sum at k plus m minus 1, we're going to write as stopping at k plus m and then removing that term manually. On the other hand, if you terminate this chain of inequalities at a value of f, we just do a comparison in the opposite order. So now, if you take this sum, but take off the first term, so now I have f of k plus 1, f of k plus 2, all the way up to f of k plus m. Okay, then that's less than or equal to the same gluing together of regions. So we've got the following here. The partial sum going from k to k plus m, if you remove that first term at index k, that's less than or equal to this integral. However, if I took the same partial sum and instead removed the last term at index k plus m, that would be bigger than or equal to this integral. F is non-negative, okay? So if the series does not converge, this series here, if I let m go to infinity, would have to go to plus infinity. And now this integral is bigger than that. So if the series diverges, then this improper integral definitely diverges as well. Conversely, if the series converges up here, then the individual term goes to 0. So as m goes to infinity, I can ignore that. And now this is less than or equal to that, and everything is non-negative, and I get convergence. So we get this claim that one piece converges if and only if the other one does. Okay, so we have convergence if and only if the other one converges. But now let's look at this inequality that we established and take the limit as m goes to infinity. Now as m goes to infinity, this becomes the series, this becomes the series, this becomes the improper integral, and this term has to go to 0, whereas this is merely a constant. So we get this right here. Subtracting the integral from every term now gives us that, on the one hand, series minus integral bigger than or equal to 0, or series minus integral less than or equal to f of k, and that was the final claim we wanted to establish. Let's see in example 5.5.14 what the integral test can be used for. Okay, so it's not just a matter of showing a series converges, but provides a very precise way to estimate the value of a series in terms of an improper integral. So for example, 1 over n squared is a convergent series. We know that from the p-test. But from the integral test, we can conclude the following. If I start this at index k plus 1, and I take away the value of this improper integral, that would be non-negative, but no larger than 1 over k plus 1 squared. And remember, the value of the series is just a finite partial sum plus this tail. Okay, so this integral is easy enough to compute. The series remainder term is right here. So the integral from k plus 1 to infinity of 1 over x squared is quick to compute as just 1 over k plus 1. Kind of omitting the details, but you can see them right there. So this term right here is just a 1 over k plus 1. So replacing it with 1 over k plus 1, now we can state that the series is the partial sum plus this tail. In other words, the tail is the series minus the partial sum. And that's going to get substituted in right there. All right, so 0 is less than or equal to series minus partial sum minus improper integral, less than or equal to what would have been the next term in the series. Okay, now we just do a little bit of manipulation. Okay, first factor the minus 1 out of these two terms. And what we're saying here is, if we can compute the kth partial sum, manually add in the value 1 over k plus 1, how far off are we from the value of the series? Well, we are bigger than or equal to 0 in this difference, so we have definitely underestimated the value. By how much? Not by more than this. So if we compute this quantity here, we are definitely under the value of the series, but not by too much. So now let's merely fix k equals 9. If we set k equals 9, we can compute 1 over 1 plus 1 over 4, etc., all the way up to 1 over 81. Then we'll add in 1 over 10, and we'll end up with about 1.6397. Compare that to the value of this series. The difference of the actual value minus what we computed is bigger than or equal to 0. So we have underestimated the actual value. However, by no more than 1 over 10 squared, or 1 over 100. In reality, this series converges to pi squared over 6, 1.6449. What we computed was a definite underestimate, but we were underestimating by no more than 0.01. So we came up with a way to pretty closely estimate the value of pi squared over 6. So the basic definitions of improper integrals, we've probably seen it before. This is almost certainly, this sort of class, almost certainly not the first time you're doing this kind of computation. Really what's crucial in this section is to show that the relevant convergence is in a sense robust. If you have two separate limits, the order doesn't matter. Also, we established the integral test for series convergence. Again, probably not the first time you've seen it. Now, what's nice about the integral test is it doesn't just tell you series converges or series diverges, but there's a nice quantitative way to estimate the error in taking a partial sum and saying, oh, if I take this partial sum and I add in a certain improper integral, I know exactly how much I'm off by, at most.